On today's episode,
the value of this private space industry went through $500 billion last year and is doubling every 3 or 4 years by projection. That's pretty impressive. So it's a big chunk of the economy now. And that is interesting because it's still pretty speculative. None of these billionaire investors like Jeff Bezos and Elon Musk, none of them are making money yet, right? It's a lost leader, their programs. They're investing for a future that hasn't yet materialized. But they're innovating and they're creating this huge activity, and they're just the most prominent examples.
Welcome to the Active Share podcast that explores less obvious investing insights in a world that's always changing. I'm your host, Hugo Scott Gall. Today I am delighted to have with me Chris Impey, a university distinguished professor with extensive experience in astronomy and education. For 17 years, he served as deputy head of the astronomy department at the University of Arizona. Currently, he holds the position of associate dean of the College of Science with over 240 refereed publications, 90 conference proceedings in astronomy, 140 educational publications, and 9 published science books. His contributions are highly regarded far and wide. He's received $20 million in grants from NASA and the NSF and has won 11 teaching awards for his outstanding work in education and technology development. Chris, thank you very much for coming on the show.
It's good to be with you, Hugo.
Great. So we are going to talk about space. We're going to talk about lots of different aspects of space, which is pretty exciting. But I thought before we get on to things like space junk, the new space race, satellites, communication, space tourism, I thought we'd start maybe with a bit about you and what drew you to the field of astrophysics and what keeps you in the field of astrophysics.
Well, I started as a physicist. My first degree is physics, and actually most professional astronomers do physics for a first degree. So it's sort of applying physics outward, if you like. Physics is the gateway drug to astronomy, if you like. So I studied physics in London at Imperial College. I went to Edinburgh for my graduate school, PhD. And then I noticed that the UK didn't have very dark and clear skies. So I thought, if I'm an astronomer, I need to be somewhere else. And so I'm in Arizona where there are 300 dark, clear nights a year. You can't beat that.
And so I hear you. I'm a resident of the UK and there's a lot of cloud. What are the specific areas of astrophysics that you've focused on? And I guess, what is it that you feel most proud of in your work, whether it's exciting discoveries or contributions to breakthroughs that you've been part of?
Sure. Well, I've focused on extragalactic astronomy or cosmology. So if it's closer than 1 billion light years away, I don't care very much. So it's a distant universe. And I suppose in 2 areas I was able to make contributions. One was the study of extremely faint galaxies, but not necessarily faint because they're far away, which would make them faint, but faint because they hadn't converted their gas into stars. So they're kind of feeble galaxies, anemic galaxies. And the reason that matters is, we tried to do a census of what the universe contains, count up all the atoms, and all the material, and we only look at the bright things. So we follow the starlight, basically. And so you can miss unevolved galaxies that haven't turned their gas into stars if you can't count them. And so I was working hard to get a full census of the dim and the bright galaxies so we can measure the matter of the universe. And then in a completely different vein, I got interested in active galaxies. Quasar is a word people are probably familiar with. And a quasar is basically a normal galaxy where a supermassive black hole in the center is devouring gas and dust. And then ironically, black holes are black, but the area around them is an incredible particle accelerator. So they can shine very brightly, their environment. And so I picked a set of active galaxies or quasars, which are pretty much the brightest objects in the universe. So these are sort of black holes that are shining. They're small objects the size of a solar system, which in astronomy is small, sitting at the middle of a galaxy and outshining the entire galaxy by a factor of 1,000. Incredibly efficient energy machines. So I studied them for quite a while.
This is an obvious, probably very dumb question, but the role of technology, I guess compute power, how has that changed and how has that sort of leveraged you in terms of what you can discover and find out now versus 10, 20, 30 years ago? Is it a completely different ball game in terms of what we can actually see?
Yes, absolutely. I mean, astronomy is sort of a discovery science where a lot of things that we found were not predicted. And so that's what makes it fun as a science. But it's also very much technology driven or technology enabled. So in those last 20 or 30 years, we've developed, when I was coming up as a PhD student or a postdoc, the biggest telescopes I could use were 6 meters, say 5, 6 meters, which sounds pretty big. But now we're building a generation of 20 to 30 meter telescopes, not a large number, 3 or 4 around the world. So these are 10, 20 times more powerful than current telescopes. So the technology to make thin mirrors and very large telescopes whose optics are incredibly accurate, that's pretty new, and it drives the field. Because when you study the distant universe, your photons starve. I mean, some of the galaxies are so far away that about one photon arrives every second, just one. I mean, it's a feeble amount of light. So you're starved for light when you look at the distant universe. It means you always want bigger and bigger telescopes. And the detector technology has improved too. People probably don't know or appreciate that the CCDs, the little devices in your phone that take pictures, are just super consumer grade, mass produced versions of sort of pioneering detectors astronomers used in the 60s and 70s. And astronomers still use sort of cutting edge versions of these optical imagers that have to be cooled to liquid nitrogen temperature, so they're very dark and quiet. So that's an example of a technology that has driven astronomy and then moved into the consumer market. And now there's 2 billion phones with little CCDs in them taking pictures.
How much of the technological innovation is deliberately around making better telescopes, or how much of it is just being adopted and adapted from elsewhere? Is it primarily done with a view to space understanding, space vision, and then has positive spillover effects that you just described? And who is paying for that?
So it is driven by that. I mean, the frontier of the field is just always hungry for more telescopes and more photons and so on. It's an interesting landscape because some of the big new telescopes are being built by consortia of universities and countries, their national governments. And then there's private money involved in some of these telescopes too. And that's a historical thing. Going back a century, the world's biggest telescopes on Mount Wilson and Mount Palomar and Yerkes Observatory in Chicago, they were funded by philanthropy. And philanthropy still plays a role in modern astronomy because there are billionaires out there who are very interested in science and some in astronomy, and they really helped it. Not just with telescopes. I mean, Yuri Milner's put $100 million into SETI to search for extraterrestrial intelligence, and there are other examples. Bill Gates has invested in these things. So astronomy kind of draws technology gurus who appreciate pure science or the curiosity-driven science of astronomy, and they want to invest in it. But the big telescopes now are going to cost $1 billion or $1.5 billion each, and so it's no single university, and sometimes not even one country, can manage to build these things.
And do you get all the access you need? Is access an issue? How does that sort of get divided up? Or is there a lot of sharing, I guess, of across countries, across groups of results?
Yeah, there's sharing, but it's brutal to get access. In Arizona, we make mirrors, thin mirrors, under our football stadium, and we make 8.4 meter mirrors. We have an oven that spins and melts the glass and spins it into a parabola shape and then cools it down. And we build those. We make mirrors for our own telescopes, and then we sell them to other people. And the mirrors are our skin in the game. So this giant Magellan telescope, which we're building in Chile, a 22.5 meter telescope, we get 10%. We will get 10% of the time on that. And our contribution is the mirrors. So other universities in the consortium just have to raise the money and put cash on the table. So you can have payment in kind. You could build a very impressive instrument that sits behind the telescope and get a share of time that way. There's various ways the time's divvied up. but it's hard to get. I mean, the oversubscription, this is true of the Hubble Space Telescope, even though it's kind of a bit long in the tooth now in its third decade. Hubble Space Telescope time is oversubscribed by 8 to 1, so 8 times more proposals than can get time. And when you're on the review panel, they're all good. I mean, there are no crappy proposals. And the big telescopes that for the ground-based observatories are the same way. There's way more good proposals and good ideas that can possibly get time on the telescope. And then it's worse than that. It's a wild card because you get your little time, like your 3 nights in July or your 2 nights in November. And if they're cloudy, bad luck. You have to come back next year. So you don't get a dispensation for the weather. You just get your nights in the schedule, and then you just have to take your chances on the weather.
Understood. And so if you look at other industries, the kind of Moore's law effect, where as we get more compute power, it's having a disproportionately positive effect on outcomes, that innovation is happening faster, whether that is in medicine, whether it is clearly in communication technology. Are we on that similar curve when it comes to space exploration, that as we get better and better technology, we're just going to learn disproportionately more, much faster, so that, if we're having this conversation in 10 years' time, do you think we really will have moved on meaningfully in either what we can see or our understanding of what we can see?
I think we will. But piece we haven't talked about is computation. So it's very much a computationally intensive field. And that's in 2 ways. There's sort of, people think about science as sort of theory. You have your theories and then you have your observations and you mash them together. But there's actually a third leg of the stool, if you like, which is computation and simulation. So we've learned a lot about the universe by simulating aspects of it in computers, and they have to be supercomputers. They have to be pretty much at the bleeding edge of computation. So just doing that simulation work, which is important because it guides both observation and theory. It's just an important part of understanding a complicated universe. That's very demanding of CPUs, of computer power. And then the data reduction is now very demanding. I mean, this new surveys being done by these big new telescopes are going to generate tens of terabytes of data a night. And because they're going to get another few tens of terabytes the next night, you have to keep shoveling. You have to reduce it and understand it every night in real time. You can't just pile it up and then, go off and study it, because you want to be alerted if something's changing, if a supernova just went off, if, an exoplanet was moving, and you could follow it up. So there's an enormous demand on computation for data reduction. And it's almost become a bottleneck at this point, because the new surveys are going to be generating so much data. And of course, the ironic thing about astronomy data is most of it's noise. When you take a picture of the sky, a deep picture of the sky, you go outside and the sky is dark at night and there are a few stars, a few thousand stars if you live in a dark place. Well, it's the same thing if you're observing distant galaxies. Most of the pixels, most of the real estate of your image is actually sky or dark sky or noise. And you have to sift out the small fraction, a few percent of the pixels where something interesting is happening. So that data filtering problem is a challenge. And we now use AI methods, machine learning, to do better with that, because there's no way humans can do it. And then overall, the computational demand is intensive. It really is, which is why people, form these big consortia and collaborate, because they need to pool their computational resources as well.
So, my next question was inevitably about AI and the current surge in this phase of AI in terms of investment. That must have big positive spillover effects to you, and I guess quantum computing as well. So if you're optimistic about what is happening in those fields, then that has very positive spillover effects to what you're doing. And in fact, I'm sure it's more circular than that. I'm sure that you're feeding into that and contributing to the innovation that's happening there. So that would make one more optimistic in terms of that kind of exponential curve.
Yes, because machine learning is having an impact on almost every field of science. The people who try and detect gravitational waves with these big detectors like LIGO are using, AI methods to try and filter out very subtle signatures, maybe of the early universe or black holes merging. People trying to find exoplanets or extrasolar planets, those signatures are also quite subtle. And so, again, large data sets, and you have to use machine learning methods, not just to find the things you know. This is the important point. You're trying to find the things you don't know. You're trying to discover new things in a field where discovery is part of the game. But how do you anticipate an interesting phenomena that you've never seen before? How do you know what's new and interesting when you don't even know quite how to define it? Machine learning's actually very good at that because it's good at identifying something that's potentially interesting without you having specified it beforehand. It's just going to be sure that it's not noise or some false flag.
So if I could bring you not back down to Earth, but closer to Earth, can we talk about the new space race? And I suppose, would you agree that that is a fair description, that there is greater investment into more space activity? And by space, we mean close to the Earth, whether that is unmanned trips to the moon, whether that is the militarization of space, whether that is the battle for communication infrastructure dominance by satellites. Do you think we're in a new space race, and why? If so, why?
Yeah, there's any number of measures that say that it's actually an extraordinary time right now in the last few years. And you take the long arc of the space program, starting with Sputnik 1957. 2 years ago was the first year where private companies had more launches to Earth orbit than governments. So that historical aspect of space, where it was originally the US and the Soviet Union, and then later the US and China and the Soviet Union and some emerging space powers, that's being completely eclipsed by the activity in the private sector, just in terms of number of launches. The value of this private space industry went through $500 billion last year and is doubling every 3 or 4 years by projection. That's pretty impressive. So it's a big chunk of the economy now. And that is interesting because it's still pretty speculative. None of these billionaire investors like Jeff Bezos and Elon Musk, none of them are making money yet, right? They're still, it's a lost leader, their programs. They're investing for a future that hasn't yet materialized. But they're innovating and they're creating this huge activity, and they're just the most prominent examples. There are probably 40 private space companies worldwide that are doing interesting and important things. And so it is really a new situation now. It's unprecedented.
And what do you think the motivation is? Earlier you said billionaires in space. It seems that when you hit $1 billion, you suddenly become obsessed with trying to live forever and then conquer space. But there must be economic motivations here. Is it to control communication infrastructure? Is it the hunt for resources that are outside of the Earth's orbit? And so that gives you some economic power. What do you think are, beyond the sort of romantic side to it, what do you think are the economic motivations, or is that too terrestrial a question?
I think there are economic motivations, as personified by Jeff Bezos of Blue Origin and Elon Musk of SpaceX. They actually have both aspects in play. So they are businessmen and they have run very successful companies, obviously. And so they have an economic model. Elon Musk he made his first money by partnering with NASA at a time when the US couldn't put an astronaut in orbit after the space shuttle was retired. It was about a decade when the US embarrassingly couldn't put one of its own astronauts into orbit without help from the Russians. Elon Musk got his first multi-billion-dollar contracts from resupplying the space station and putting Americans up there. Now he's going to put tourists up there. I'm not sure the tourist revenue is going to be very significant for a while, but he also is very well aware of the resources on the moon and Mars, especially in the moon in terms of industrial resources. And so, they do have their eye on an actual economic model for the future, but they're also driven by this visionary thing. Elon Musk has said famously, he says a lot of things. He wants to die on Mars, and he's dead set on Mars, which is really difficult. I mean, 100 times further away than the moon, much, much more difficult in terms of setting up the minimal infrastructure for a base. And so that's a real stretch goal for him. Jeff Bezos similarly has this sort of interplanetary vision, this almost misty Star Trek driven. This is an ironic aside. Some commentators have noted how in his physical appearance, Jeff Bezos has been trying to make himself look like Jean-Luc Picard, his hero. So they do have that sort of misty romantic vision while they're still also playing out what they think is a real plan to make money and make revenue and mine resources in space and set up a real economic enterprise in space.
But I guess we've seen in the Russia-Ukraine war the role of Starlink, Elon Musk's company that has provided pretty critical communication infrastructure to Ukraine, but also at points has turned it off as well. So it gives him a US citizen. It gives him a tremendous amount of power elsewhere in the world. So it would seem that there clearly is it a desire to create a hard to replicate communication network, or is it a desire to acquire power? But that's certainly, as technology changes, if you can control communication systems that leapfrog ones that are more physical and based on Earth, then it clearly is, I guess, both economic and power driven.
Yeah, he's found a very important niche through these constellations of satellites, these small satellites, you can call them nanosats if you want, tens of thousands of them, projecting in the next few years. They are primarily designed to deliver high-speed internet to parts of the developing world and that don't have it. And then, yes, leapfrogging over the sort of history of cable and wires that we did in the industrialized West countries did before they went wireless. And it's it's almost that sounds like an altruistic goal. You're bringing internet to people who've never had it before, and that they will benefit from it in their lives and in their livelihoods. But there is a lot of power that goes with that, because when you control the satellites, yes, you can switch them off, or you can control the rate at which you launch them. That particular activity is since I'm an astronomer, that has a little downside, which is those satellites are pretty bright. And when the sun's low on the horizon at dusk or dawn, they create these streaks across the sky that are really messing up pictures from the Hubble Space Telescope and James Webb, and they will mess up even more the big telescopes that we're building now. So the sky is getting light polluted because of these constellations of satellites.
That's interesting. So why do you think countries like India want to go to the moon? What's in it, apart from bragging rights, which are a little bit, the US has already landed on the moon? What's in it apart from bragging rights?
I think for India, there's clearly a chauvinistic, there's a national pride associated with being a spacefaring country. And they should rightly be proud. They have a very impressive technical workforce, and we tend to only associate that with computer programmers and certain types of tech industry. But they've got, very good space scientists too, and they've developed some capabilities that are pretty impressive from a standing start. In the personified in the current Indian government, I think that the national pride issue is front and center. Clearly, there's no obvious economic benefit for that still developing country doing the space activity. But just to say that they're sitting at the table with just a handful of countries, Russia, China, and the US, who've been to the moon and might go to Mars and so on. I mean, that's a big deal for them. So I think that really does motivate it.
Yeah. And do you think warfare, we're in a world that's gone from arguably maybe unipolar to multipolar, and who knows how geopolitics unfolds, but is a decentralized world feeding into a sort of decentralized space system, and that the US has its GPS system, China has its own, maybe India develops its own? Is space in some ways an enabler of a decentralized world that's pulling apart geopolitically?
Yeah, I think it can be, and part of the reason for that is that space is kind of the Wild West. I live in the Wild West, and space is the new Wild West because it's almost unregulated, and the legal backdrop for activities in space is almost non-existent. There's only ever been two United Nations treaties that dealt with space, and they didn't answer most of the questions that need answering now, which is who owns what and who's liable for what when things go wrong. The Outer Space Treaty of 1965 did talk about weapons in space, and that's really important. But even then, there's concern that maybe China, whose space program is so entwined with the military-industrial complex that you can't separate them. It's quite secretive. There's genuine concern that the Chinese might, start putting weapons up in space. And we've already seen countries shoot down their own satellites, just test anti-satellite technology, which is an intensely antisocial act, because when the Chinese and the Russians each did that, they created thousands of pieces of space debris, any one of which could take out a satellite or a space station.
Well, that's something I wanted to ask you about: space junk, space debris. How crowded is it getting out there? How much risk is there from bits of debris that could wipe out maybe things like GPS, or even worse, could affect climate?
Yeah, it's getting worse rapidly. It's been characterized as a tragedy of the commons, where everyone benefits from the low Earth orbit activity, but no one's really incentivized to take care of problems that arise from that activity, and so it doesn't get taken care of. So then, just the sheer number of satellites or objects in low Earth orbit is doubling every couple of years, and we're really heading towards possibly 100,000 by the end of this decade, by 2030. And that's from a current number that's more like 12 or 13,000. So that's an incredible increase. And the collision rate just goes up proportionately. And then all the stuff that was already up there is degrading and sometimes falls apart. And every collision creates pieces which can collide with other pieces. As a NASA scientist in 1979, Kessler wrote a paper with this dire scenario where the exponentiation of creation of debris renders low Earth orbit unusable. And people back in 1979, that just was a theoretical calculation. But now people wonder, wow, that actually could happen. So there's genuine concern about space debris. The astronauts or the space station astronauts pretty much have to shelter in the central hub every month or so because of a possible impact of the space station. And the frequency of these events that could affect astronauts who are up there is steadily increasing, and we can measure it. So the problem is real.
And as you said, around regulation, there's no obvious solution to that until something bad happens, and then there's a response. Is that likely how it unfolds?
I'm afraid so, just because the United Nations works on sort of geological or glacial timescales. So apart from the Outer Space Treaty, which dealt with weapons in space, and also did say that countries couldn't own the moon, there's only ever been one other treaty, the Moon Treaty of 1979, and that did talk about ownership, but wasn't signed by any of the spacefaring powers. And neither of those treaties talked about commercial entities or private individuals. They only talked about governments. So there's no legal context for resolving disputes between nations in space. And the UN has a working group that's been in operation for 50 years that is currently considering, that has released probably a dozen or so guidelines, totally non-binding, voluntary guidelines for space junk, dealing with liability issues, dealing with conflicts. But until they get a new space treaty that the major powers sign, there's no teeth to it. So it's self-regulation at this point, and each country has its own interests, and they don't always overlap.
One more sort of economic question, and then we'll talk about a future off Earth. Do you think the idea of space mining, that there are meaningful resources that can be extracted and brought back to Earth in a meaningful time frame, do you think that's just wishful thinking?
I think that is a little beyond the horizon. It's indisputable that there are near-Earth asteroids that are half a kilometer in size typically, and if you judiciously select one of those, you would have at current market values maybe $2 trillion worth of precious metals and similar number for rare earths, valuable commodities, and they're commodities that are often on Earth in certain people's hands and certain countries' hands, so they're not always available to the countries that want them. And we do have the technology. NASA knows how to steer things in space. We can attach rockets to asteroids, so we could bring an asteroid into a Earth-Moon captured orbit and then mine it at leisure. But there's the rub. Once you've got the asteroid in Earth-Moon orbit, say, set up a mining operation, nobody's really costed out how much it will cost to deliver the material to the Earth. And it may not be a good economic model. Nobody knows. Also, there's the classic, the Hunt brothers problem with silver, that you could flood the market and crater the price and ruin your own economic model. So I think, to answer your question, I think mining asteroids is technically feasible, and there's a very broad economic argument to be made for it, but the devil is very much in the details of the mining and the retrieval. And so I'm thinking 20, 30, 40 years before that's viable. And like in many industries, the first people doing it may well lose their shirts.
Mm-hmm. Yeah. That's interesting, actually. Your 20, 30, 40 years was maybe sooner than I was thinking. Future off Earth, do you think that's likely? Do you think that you really can? We talked about Musk wants to die on Mars, or try and avoid dying on the way to Mars. Human life existing outside of Earth, is that really likely? Is it really possible based on current technology?
I think it is going to happen, but not maybe on the time scales. Musk's time scales are hopelessly unrealistic when he quotes, a goal like with his Starship and so on. But on the other hand, his technology is impressive, and he may get there in the end. So off Earth, habitation, viable, self-contained bases, yeah, I think it actually will happen, but it just won't happen around the corner. People forget. Space is an extremely hostile, unforgiving environment. We were not made to be in space. The radiation, the fact that you have to have all your resources there, it's too expensive to ship things to the moon even, let alone Mars. So you have to live off the land. Now, the good news about that is the technologies to do so are also well proven and exist. You can take Martian soil and use electrochemical methods to turn it into slump block and make a hardened shelter that will protect you from cosmic rays and radiation. You can take that same soil and extract water from it to drink. You can take oxygen from it, separate the water into hydrogen and oxygen, make rocket fuel. So all the things you need, assuming you can grow food, are there. So you don't have to bring it with you. But the infrastructure just for a minimal viable base is enormous. And it's going to happen on the moon first, of course, because it's much closer. Another piece of this is 3D printing, which has also been moving very rapidly. And so you're going to have robots and 3D printing fabricating a lot of these first settlements without having to involve large crews of astronauts and people and construction workers, if you like. So there's ways to make it more efficient. But Mars and the moon are totally different beasts. Mars is, like I said, depending on the route you take, it's 100 times further away. Just to have the first humans on Mars, people don't talk about it very much. You've got an 8-month trip there to use the least amount of rocket fuel, and then an 8-month trip back, and maybe you spend a few weeks or a month there. You're not going to live there. So you have to send a spaceship with maybe 4 astronauts or whatever, with close to 2 years worth of food, water, and supplies. That's a pretty big spaceship. That's Elon Musk's Starship. Maybe not even his Starship's big enough. So just getting to Mars the first time, put a little footprint there and stay for a while, is a huge undertaking. The moon is so much more tractable. It's only a week away, 250,000 miles. You can resupply it fairly quickly. So I think it'll happen on the moon. It's just less glamorous, of course. And then there's the geopolitical angle. We know that the Chinese have done some pretty impressive things in the last few years. They're close to completing a space station, which will be complete around the time the International Space Station may actually be deorbited. The Russians have pulled out, and there's a lot of countries that are no longer that interested in it. So the Chinese are going to go to the moon and go to Mars by their public statements, and there's no reason to doubt it. Their space program is growing at the rate of their economy, which is not as fast as it has been. Their space program was doubling every 3 or 4 years when their economy was booming, and now it's slowed down a little, but they're still investing a huge amount of money in it. And they have the geopolitical motive, of course. They want to show that they are the world's great superpower of the future. And to them, that means a lot of things on the Earth, but it also means being off Earth too.
Would you, if it were possible and had been tested, would you, if someone invited you to go to Mars, would you accept?
I don't know if I'd go to Mars. I mean, not just the risk, it's just a huge commitment. And of course it's extremely risky. I mean, I do Richard Branson's, $250,000 nosebleed, 7 minutes, zero gravity. I might go to the moon, not that I could afford it, but that would be an interesting thing to do. But I'm not sure I'd go to Mars. There are plenty of people who would go. I mean, NASA had a one-way trip model because the cost of going to Mars they knew was so high, and that got out and that got sort of published in the media, and that was slightly embarrassing for them to admit that they had a one-way Mars trip plan, and they had no shortage of people who were willing. And we know there's no shortage of people who would be willing to volunteer for a one-way trip. We're all going to die, and dying on Mars, as Elon Musk might point out to us, is a pretty spectacular way to go.
Uh-huh. You serve on the advisory council of METI, Messaging Extraterrestrial Intelligence. Could you talk about a bit about that? Because I don't know what that is. My literal interpretation is it is what it says it is, which is trying to find signs of life outside of the Earth. Is that what it is? Have I missed something? And next, my follow-on question would be: do you think there are sentient beings? There is life elsewhere? I mean, I know it's a sort of obvious, basic question, but I think I have to ask it.
Sure. So METI is an offshoot of SETI. So SETI is the search for extraterrestrial intelligence, and that's basically a listening experiment using radio telescopes. Traditionally started in 1959 with Frank Drake at the Radio Observatory in Virginia, and that's just essentially using radio telescopes to listen for signals that have to have an artificial origin. They're pulsed, or they contain a message, and they don't have a natural astrophysical cause. SETI extended to optical methods because a civilization with lasers could pulse lasers that actually pulse lasers efficiently enough to outshine their parent star for short periods of time. We could do that. So SETI's been around for decades. They've never found anything, never heard anything that's irrefutably of alien origin. And METI is the counterpart to SETI. It just says, well, not just do the listening experiment, let's do the communication experiment. Let's send a message. And it's mostly an intellectual exercise of what message would you send? How would you conceive of a message that was meaningful to an alien of unknown function and form, right? So that's quite a challenge, actually. You can't assume language, you can't assume culture, you can't really assume anything. The biology may be totally different too. So it's quite challenging. The simple answer is you do math. So you send out mathematics, mathematical theorems or prime number sequence or whatever it might be to show that you understand mathematics, and you assume mathematics is universal. So, but there's a whole discussion, and that's the discussion we have. And I should say it's controversial in some part because before he died, Stephen Hawking famously said we shouldn't message the aliens because they might be malign and they might destroy us. So why would we take that chance? The answer to that from the group I'm in is that, first of all, it's mostly just a design exercise. And also the few experiments that have been done are not of any proximate danger, so that because the targets are hundreds or thousands of light years away. So it's centuries or millennia before, you even make contact in principle. And to your second question of what the odds are that it's a worthwhile exercise at all, it's basically a numbers game. That one of astronomy's great successes in the last few decades is the discovery of exoplanets, planets around other stars. And we're now up at about 5,800 that are confirmed. And you can project the numbers pretty reliably across the Milky Way. And we also know that many of these exoplanets are Earth-like or nearly Earth-like. And so they're habitable in the sense that they could have liquid water, they have energy source for life from their star, and they have carbon-rich material that's everywhere. So that number is at 10 to 20 billion habitable worlds in the galaxy. So that's a pretty large number of potential biological experiments. So it seems implausible that all of them are stillborn or none of them ever developed biology, because it happened on Earth pretty quickly after the Earth formed. And the real estate of time is interesting too, because the first, if you look around the galaxy, the earliest Earth clone, if such a thing exists, and it probably does, could have formed 8 billion years before the Earth formed, because the Earth formed, well into the history of the universe. So you could have an Earth-like planet with its biology getting its start, and it has billions of years head start on us. Now, what would that lead to? That's amazing. And so the logic there is, it seems statistically unlikely that there's no life out there. It's also statistically unlikely that we're the most advanced or the first creatures to attain our level of intelligence and technology. And if you believe those arguments, which of course are not watertight, you need evidence to make them real. They're just general arguments. Then these are worthwhile things to listen for signals and send signals in the hope of making contact.
Great. Well, look, that's a great place to end. And I just want to say thank you for coming on. It's been fascinating. I've learned a lot. And I think I sort of, in your bio, said where to find you. I guess we know we're not going to find you on Mars because you're not going to go. But I very much enjoyed our conversation. Thanks for coming on. Thank you again.
Sure. I enjoyed the questions. It was fun discussion. Thank you, Hugo.
Brilliant. Well, thank you, Chris. Thank you very much.
Okay. Bye.
Bye-bye. Thank you for listening to today's episode of The Active Share. The Active Share is available on iTunes, Stitcher, Google Podcasts, TuneIn, and Spotify. And if you'd like, please leave us a review. To hear additional insights from William Blair Investment Management, visit us at active.williamblair.com and follow us on Instagram at WilliamBlairIM.
This content is for informational and educational purposes only and is not intended as investment advice or a recommendation to buy or sell any security or to adopt any investment strategy. Investment advice and recommendations can be provided only after careful consideration of investors' objectives, guidelines, and restrictions. The views and opinions expressed are those of the speakers as of the date of this recording, are subject to change without notice as economic and market conditions dictate, and may not reflect the views and opinions of other investment teams within William Blair Investment Management. Factual information has been obtained from sources we believe to be reliable, but its accuracy, completeness, or interpretation cannot be guaranteed. Any discussion of particular topics is not meant to be comprehensive and may be subject to change. This material may include forecasts, estimates, outlooks, projections, and other forward-looking statements. Due to a variety of factors, actual events may differ significantly from those presented. Past performance is not indicative of future results. Investing involves risk, including the possible loss of principal. Any investment or strategy mentioned herein may not be suitable for every investor. References to specific companies are for illustrative purposes only and should not be construed as investment advice or a recommendation to buy or sell any security. William Blair Investment Management may or may not own any securities of the companies referenced. It should not be assumed that any investment in the companies referenced was or will be profitable.